Hi, this is Alex from devstories.eu. LangGraph, episode 16 of 18. If an expert sub-agent is called twice in a single conversation, should it remember the first call or start fresh with total amnesia? That choice changes everything about how multi-agent systems behave, and it is controlled entirely by subgraph persistence and multi-agent patterns. When you build a parent graph that routes tasks to subgraphs, state management gets complicated. Think of a primary customer service bot that handles general chat. When a user asks a complex question about an invoice, the primary bot routes the request to a dedicated billing expert subgraph. By default, subgraphs are entirely stateless. When you compile that billing expert without specifying a checkpointer, it operates strictly on a per-invocation basis. The primary bot hands it the required inputs, the expert runs its internal steps, returns a result, and immediately discards its internal state. If the user asks a follow-up billing question 5 minutes later, the primary bot calls the expert again. The expert has no memory of the previous exchange. It starts completely fresh. For a simple data extraction subgraph, that amnesia is perfectly fine. For an interactive, specialized agent, it is incredibly frustrating for the user. To fix this, the expert needs its own memory across turns. A very common mistake here is passing a brand new checkpointer instance, like a memory saver object, directly into the subgraph's compile method. Do not do this unless you want the subgraph to share the exact same state across completely different users and sessions. If user A and user B both talk to the system at the same time, passing an explicit checkpointer instance to the subgraph means their data gets mashed together into one global state. This creates massive crosstalk between isolated parent threads. Instead, you just pass the Boolean value true to the checkpointer argument when you compile the subgraph. This is where it gets interesting. Setting it to true tells the subgraph to rely on the parent graph's checkpointer mechanism, but to maintain a completely isolated multi-turn history specifically for itself. Behind the scenes, the framework handles the namespacing. It automatically creates a unique thread ID for the subgraph that is permanently tied to the parent's thread ID. Now, look at the billing expert scenario again with this configuration. The user asks an invoice question. The primary bot routes it to the expert. The expert answers and goes dormant. Later in the same conversation, the user asks a follow-up. The primary bot routes back to the expert. Because it was compiled with the checkpointer set to true, the expert wakes up, checks its dedicated subthread, and loads the context of the invoice from the earlier turn. It acts like a persistent participant in the conversation. And because that subthread is strictly scoped to the parent's thread, a different user talking to the system gets their own completely clean instance of the billing expert. The way you configure a subgraph's checkpointer dictates its entire identity in your system. Leaving it blank creates a disposable, stateless utility function, while setting it to true creates a continuous, context-aware collaborator. Thanks for spending a few minutes with me. Until next time, take it easy.